Hello, ma'am. What name have you joined in as?
Yes, good afternoon, everyone. Sorry for the interruption and for the late starting of the class. Due to some network issues, we couldn't start on time. Anyway, we have fixed the issues, no problem now. So, in the last class, I think you have all seen the Booth's multiplication and other arithmetic and logic things which are there. Okay. So in this class, we are going to see the binary representations of floating point numbers, and computer representation of floating point numbers, as well as floating point instructions. So hope I'm audible to everybody. Yeah, this is unit 2. Okay. So this is the last topics, with the last three topics which we are having in our unit 2. As you know, again at 4 to 5, 4:20 to 5:20, we are having another class. So with that, we will be finishing the unit 2. Okay, fine. So hope my voice is audible.
Gandhi sir, sorry for the interruption. You need to share your screen.
Yes, yes. I have not yet started. I am just waiting for the reply
Okay.
from
Yes,
students
sir.
whether I'm audible.
Okay. Yes.
Yeah. Is my screen visible? Yeah, I hope my screen is visible, right? Okay, so yeah, well, so today's topic is about binary representation of floating point numbers and computer representation of floating point numbers, as well as floating point instructions, right? So we will see what are those. Sir, చెప్పండి. Okay, so as we know, whatever data we give to the system, everything is being sent in, or it is understandable only in binary numbers, right? So binary representation. So whatever floating point numbers are there, how we are going to represent these floating point numbers in binary representation, we are going to see here. I'm just trying to remove this window, but there is some problem here. So please try to ignore it. Okay, because I don't want to waste time. Already we wasted nearly of 20 minutes, right? Okay, so see here, you can see a decimal fraction of this form. Now we want to convert this particular, we want to convert this to a binary fraction of this form, right? So this is a binary, this is a decimal number, decimal fraction, and we are going to convert it to the binary fraction, right? So for that, we are going for different algorithms. Just give me a minute. I think I'm getting some problem here. Yeah. Yes. So see the algorithm for conversion. See the algorithm for conversion. So here you can see that what are decimal fraction we are taking. So taking that as, we are taking, let x, we are considering it as x. Okay. So let x be a decimal fraction. So this is x, right? So you have to convert each and every number to binary, right? So you need a loop for that one. So you're saying you're starting with the first number I equals to 1, and you're repeating until x equals to the required number, right? So you're starting from repeat until x equals to 0 or I equals to the required number of the binary fractional digit, right? So what is y? What is y? Y equals to x into 2, right? Okay, y is equal to x into 2, and x is nothing but the fractional part of y, right? X equals to the fractional part of y, and you're taking b of y is nothing but the integer part of y, and each and every loop you have to, I mean, every time you are using your particular loop, you have to increment your particular value. So you are saying I equals to I plus 1, right? You're saying I equals to I plus 1. It is just like very simple, like you're in a C program. You're saying y equals to, if you want to add numbers from the first 10 numbers. So what you do? You take the loop, right? You give a particular sum, you say y equals to, or sum equals to sum plus 0 or something, or sum plus I, sorry, sum plus I, and at the last you say I plus plus, right? So each and every time it will be incrementing. Okay. So in the same way, oh, God. Well, okay. So in the same way, we are going for this particular algorithm. So we are going to see an example for this. So you are converting 0.75 to binary. So you are taking this number as x. So you are saying x equals to 0.75, the initial value, and you are saying x into 2. So what is x? 0.75 into 2, that is 1.50, right? And again, you go on until you require your required value. So again, this is taken as x, 1.50 into 2, that is 1. Okay, and you go on until you get the particular value. Until whichever value you want, you go on incrementing your value. That's what it is given in the algorithm. I equals to I plus 1, right? I equals to I plus 1. Okay, so we go on the same way. Thus, the binary representation for 0.75 is thus 0.b1b2 equals to 0.11b. Okay. Yes, this is another example. In the binary representation, so b1 represents to the power of -1, b2 represents to the power of -2, and so on until bm, which represents to the power of -m, that is 1 by to the power of m, right? So 0.11 binary represents to the power of -1 plus to the power of -2, which gives you 1 by 2 plus 1.4, that is 3.5, that is equals to 0.75. Please try to concentrate. If you miss anywhere, you may not understand. Okay. So the value of 2 power of -1, I again repeat. So in the binary representation, you're taking the 0.b1, b2, and so on till bm, where b1 is represented as to the power of -1, and b2 is represented as to the power of -2, and so on until bm represents to the power of -m. So to the power of -1 is nothing but 1 by 2, to the power of -2 is nothing but 1 by 4, and so on. So if you want to represent 0.11, it is represented as to the power of -1 plus to the power of -2. So to the power of -1 is nothing but 1 by 2, and to the power of -2 is nothing but 1 by 4. So you are adding it, you are getting 3 by 4, which is nothing but 0.75, right? So in the same way, convert the decimal value 4.9 into binary, right? So as you go on like this, we get this value. Okay. Yes. Again, another example. You're taking 0.9, 0.9. the value of x. So convert the fractional part into binary using multiplication by 2. So you are saying 0.9. So 0.9 into 2, that is 1.8. Okay. So here the when it is 1.8, this is taken as b1, right? So b1 equals to 1, and 0.8 is taken as x, this fractional value, right? So x is the fractional value, right? So in the same way here, you're saying again x into 2, that is you're getting 1.6. So if you take 1.6, b2 is 1 and x is 0.6. So you're saying x into 2, then b3 will be 1 and x will be 0.2. In the same way, here 0 is the b4 value and 0.4 is the x value. Here again 0 is the b5 value and 0.8 is the x value. Thus it repeats. Okay. Yeah. Since x is now repeating the value 0.8, we know the representation will repeat. The process is repeating it every time, right? It goes on like this. Okay, so here it is 1 1 1 0 0 0 0 0. Okay, 0 1 1 0 0 1 1 0 0 and so on. Okay, do this again. Okay. Okay, fine. Yeah, don't need to worry. If you're not understanding, we will again revise it. Okay, but for now, please try to follow what I'm telling. You may get some doubts, but when you do it in practice, we'll be giving you any practical questions anyway. So when you do it in practice, you will come to know what it is. Okay. So this is how we are going for a binary representation, right? Yes. Yeah, somebody was asking in slide 5, sir, 1.50 into 2. How is it 1, sir, in slide 5? It is not 1.5 into 2. It is 0.75 into 2. The value of x is 0.75. Please ignore this one. I'm trying to take out this one, but I don't know why I'm getting this particular problem. Please ignore this one. Okay. Please stay attentive in what I am telling. Okay. So the value of x is here 0.75. That is the initial value. And as I am incrementing the value, I am taking this 0.75 here. This x value 0.75 into 2, that is 1.50. Okay. Now this value is taken as b1 and the fractional value is taken as x equals to 0.5. In the same way, now the value of x is 1.50. I am taking x into 2. So 1.50 into 2 is 1.0. So this 1 is taken as b2 and this 0 is taken as x 0.0. Okay. So the binary representation of 0.75 is nothing but 0 point B1 B2. What is B1? 1. What is B2? 1 equals to 0.11 B. Okay. So B here is the initial value. You are not having anything here. Okay. Hope you understood. Right. So that's how we are going for a floating representation. Right. So I am again repeating what we have done till now. So what you are doing here is you are converting the decimal fractions into binary representation. Right. Consider a decimal fraction of the form 0.d1, d2 and so on to dn. This is just a decimal fraction which you are considering. Now, if we want to convert this to a binary fraction of the form 0.b1, b2, bn using binary digits instead of decimal digits. So here you can see this is a decimal fraction representing 0.d1, d2 and so on to dn, d for donkey, right, into what binary function, binary fraction, that is 0.b1, b2, bn, b for buffalo. Okay, there's a lot of difference here. Or you can think this is as D decimal and B binary. Okay, to make you understand, or maybe my pronunciation is not clear to you, I told you that D for donkey and B for buffalo. Okay, you can remember it as D for decimal and B for binary. Okay, but to make you understand, more understandable, I told D for donkey and B for buffalo. Okay, right. Now, what we are doing? We are going for a algorithm. So what you are going to do? You are taking the decimal numbers and converting into binary number. So I am taking the decimal fraction here. Let x be the decimal fraction 0.d1, d2 and so on to dn. Now you are taking the initial value x. Am I right? I am taking the initial value x. And I am taking that initial value x and I am multiplying it with 2 because I have to convert it to binary. Right? So when I multiply it with 2, I get a fractional part. So that fractional part is x. Right? And the binary part is bi. Integer part is called is represented as bi. Okay, and you increment it. So for incrementing, you are saying I equals to I plus 1. So I hope you understood this algorithm. Now we are going to implement this algorithm only with an example here. I'm saying x equals to 0.75. You are converting this to binary. It is a decimal number. You are converting into binary. So to convert into binary, what you are doing? You have to multiply with 2 according to the algorithm which we have seen here. Multiply it with 2. So I am multiplying it with 2. 0.75 is the initial value. I am saying 0.75 into 2. That is 1.50. Now according to the algorithm, I am saying x is the fractional part. Yes. So what is the fractional part here? 0.50. Am I right? 0.50 is the fractional part, that is x. And 1 is the, what is 1? Integer part, that is bi. So this is the bi in the sense b1. This is the integer part. So I am saying b1 equals to 1 and fractional part x equals to 0.5. And I am saying I equals to I plus 1. Am I right? Here in last one I am saying I equals to I plus 1. Now what happens? This value is taken as x now. That is multiplied. You are again repeating the loop. 1.5 into 2. So 1. Now again the binary part is taken as b2, that is 1, and the decimal part 0.0 is taken as x. Thus the binary representation of 0.75 is given as 0.b1 b2. 0. What is b1? 1. Right? What is b2 again here? 1. So the conversion of 0.75 into binary is represented as 0.11. Hope now it is clear. Right? So So you are taking, so if you want to convert it into vice versa, so what we have seen here, you have converted the binary, you have converted the decimal to binary. Now I want to convert the binary to decimal. Then what I have to do? This only I have to do. What I will do? In the binary representation, okay, I'll be having a number that is B1, B2. Before we have seen what is B1 and B2 here, 1 and 1, right? So B1 represents to the power of -1 and B2 represents to the power of -2 and so on to Bm represent to the power of -m. So 0.11, yes, 0.11 binary represents nothing but you have to add to the power of -1 plus to the power of -2 because it's after point, so you're adding it to the power of -1 plus to the power of -2. So to the power of -1 is 1 by 2, to the power of -2 is 1 by 4. This gives you 3 by 4, that's nothing but 0.75. So you can confirm whether you're right or wrong here easily. Okay, hope it is clear now. Okay, shall I move to the next slide? Next topic. Sir, can you explain fourth slide once? I hope I have already explained it. Still, if you have any doubt, please let me know. Why there is understood. Okay, thank you very much. Thank you. Okay, right. So in the same way, example 2, so you can work it out by yourself. Okay, right. So next topic, we are going for computer representation of floating point numbers. Right, floating point numbers. So see carefully. In the CPU, a 32-bit floating point number is represented using IEEE standard format as follows. Okay, that means a floating point number is being represented in this particular format. This particular format is called to be IEEE format. Now, what is IEEE format? Can anyone tell me? It is very important for computer science students to know what is IEEE. Can anybody answer me? What is the full form of IEEE? Yes, can anybody tell me what is IEEE? Okay, I have not got any response from you people. I think nobody is attentive in the class. I think nobody is attentive in the class. I need some response from somebody. What is IEEE? It is very important. You must know. Well, anyway, I cannot wait for your answer more. I have given you a lot of time anyway. Yes, so what is IEEE is nothing but it is Institute of Electrical. Please note that one. Yeah, yes, 8Q. 8Q, you have given the full, you have given the correct answer. Good. Hope only you are attentive in the class. Nobody is there in the class. Because I am getting only response from you, but nobody else. Either you people are not attentive in the class, or maybe you are not listening the class. Well, let us continue with the class. So why I'm stressing IEEE means because it is very important for us, for our computer science students to know what is IEEE. So IEEE, the standards which have been given of formats. Okay, even when you are writing some particular going for some ASCII codes also, I hope you all know what is ASCII codes. So what is ASCII code? I hope you all will know. In the same way, a particular format is being given by IEEE. Anyway, coming back to our subject. So a 32-bit floating point number is represented in this way. S, exponent and mantissa. So what is S? What is exponent? What is mantissa? Where S is 1 bit, the exponent is 8 bits, and mantissa is 23 bits. This size. But what are those? We will see. Yes, the mantissa represents the leading significant bits in the number. The mantissa represents the leading significant bits in the number. The exponent is used to adjust the position of the binary point, or in simple to say, the decimal numbers are called to be the exponents. Right? You say 10 to the power of 2. What do you mean 10 to the power of 2? Or you say 10 to the power of minus 2? Right? To adjust the decimal points, you are having an exponent. Clear? Okay. The mantissa is said to be normalized when it is expressed as a value between 1 and 2. That is, the mantissa would be in the form 1 point so and so and so, xxxx. Right? The leading integer of the binary representation is not stored. Since it is always a 1, it cannot be easily restored. Yes, then what is S? The S bit is used as a sign bit and indicates whether the value represented is positive or negative. Right? In the previous classes, you have seen what is a negative number, what is a positive number. I think previously Spandana madam explained you already. So where you are going for a 0, where you are going for a 1. So if it is positive, what sign we are going to use? If it is negative, what sign we are going to use? Yes. Okay. Your voice is a bit lagging in the middle, or my internet is bad, I guess. Okay, I'm sorry. 1293. Okay. Yeah, I hope I'm clear now. If there is any problem, I will try to rectify. Anyway, yeah. Yes, 52Z. Positive or yes, 0 is for positive. Okay. 561. Yes. And 1 is for 0 is for positive. Yes. Right. And 1 is for negative. 2Z. Yes. 5P. Yes. Right. People are right. MSB. Yes. So what is MSB? What is the meaning of, what is the full form of MSB? Most significant bit, right? What is LSB? Least significant bit, right? 8W. Very good. Yes, yes. Yes, good. I hope many of you people are following the class. Yes, thank you. Thank you for your response. Yes, so please keep that in your mind, okay? Then only you will understand all this. Fine. Coming back to our particular topic. Yes, so we have seen what is S, what is exponent, what is mantissa. So S is the signed bit, it may be 0 or 1. Exponent is where you are going to adjust the decimal numbers, and mantissa is the leading significant bit, right? Where S is only 1 bit of size, exponent is of 8 bits, and mantissa. Yes. Yeah. So the mantissa is said to be in this particular format 1.xxxxx. That x is nothing but some numbers, some fractional numbers which you are going to see. The leading integer of the binary representation is not stored because it is always a 1. Okay. Yes, the yes bit is used as sign bit. It indicates whether value is positive or negative. That's what we have seen till now. If a number is smaller than 1, normalizing the mantissa will produce a negative exponent. But 127 is added to all exponents in the floating point representations, allowing all exponents to be represented by a positive number. Please try to understand. You will see it practically anyway. Okay, yeah, example 1. See, represent this particular decimal value 2.5 in 32 floating point format. Yes, so this is just like previously what you have seen. 2.5 is nothing but equal to 10.1 binary bits. So the mantissa M is this one 0, 1, 0, 0, 0, 0, 0, 0 and so on. Because mantissa is of 23 bits. We have seen previously, am I right? Yes, mantissa is of 23 bits. So that only I have represented here. Yes, here it is only 0, 1, that is 0, 1, and all the other 21 bits are represented with 0. Then what is the exponent? Exponent is 1 plus 127, 128, nothing but 10000B. The sign S is 0. Because it is positive, it is 0. So you are representing 2.5 in 32-bit floating point like this. So this you are representing it here from here. Okay, and this left side, whatever is there, is this one. Okay, hope you understood. Try to analyze it. Okay, if not, anyway, we can go for a practical session anyway. Every evening we are having a class, right? In the same way, we are going for a vice versa now. What you have seen here, you are going for decimal value. Give me a minute. Yes. Sorry for the interruption. Yeah. Okay. Yeah. So what you have done here, you are representing the decimal value 2.5 in 32-bit floating point like this. Now we are going for the vice versa, right? Hope you understood. Okay, so these are two exercises which you can do. Please take it down. Please work it out. If you understood, even if you have not understood also, please try to work it out and let me know what answers you have got in the evening session. No problem whether you have not understood the problem. Just try to go on. Whatever you understood, you try to keep it on paper. Please remember, problems are understood only when you write it on the paper. Simply analyzing it on the screen or on the PPT or in the online class will not work out. Okay. The next topic is floating point instructions. This we will see in the evening class. Okay. So I just want to summarize what we have discussed till now. Okay. So first thing is that we are going to go for binary representation of floating point numbers. So for that I am going for an algorithm for conversion. So in the algorithm, I am taking the decimal fraction as 0.d1, d2, and so on to dn. I am taking a loop starting with 1, and then I am repeating my loop. After that, I am multiplying the particular decimal value with 2 because I have to convert it to binary. And I am taking x, where x is the fractional part and b is the binary part. And I have to increment the particular loop. So I am saying I equals to I plus 1. So in that same concept, I am taking my number as 0.75. I multiply with 2 and whatever value I am getting, I am taking the initial value, that is nothing, sorry, not the initial value. I am taking the binary value as b1 and the fractional value as x. Now whatever binary value I have taken, I am representing that as the binary representation for the initial value. So for the same thing we have done, and now we are going for vice versa. So vice versa in the sense we are having a decimal number, sorry, we are having a binary number, we are converting into decimal number. So in that case, if you are having 0.11, so from the left side onwards, you multiply it and add the two numbers. So b2 into 2 to the power of minus 1 plus b1 into 2 to the power of minus 2. So that's what I have done here. In this case, I am getting my number. This is about this thing. Next, I am going for the, okay, this is one other example. You can take down this one also and please try to work it out. Convert the decimal value 4.9 into binary. Well, yeah. Next, we have gone for this computer representation of floating point numbers, right? Yes. So in this, we are having this format which is being represented by I giving format is given by IEEE, and there we are having the S exponent and mantissa, where S is nothing but the signed bit, it may be 0 or 1. Next one is the exponent, where the exponent is nothing but the particular number which is used to adjust the decimal numbers, and the mantissa is nothing but the particular binary number. And the size of S is 1 bit, exponent is of 8 bits, and mantissa is of 23 bits. So in that case, I'm going to take an example here. Yes, I'm taking an example here, 2.5. In the normalized form, it is nothing but 1.01 into 2 power of 1. So the mantissa is nothing but, because I'm having here 1.01. So because M is the mantissa, it is of 23 bits. So in that 23 bits, the first two bits are 0, 1, and all the other bits are 0, 0, 0. Right? Next, the exponent. So here, as given, 127 is added to all the exponents, right? So I am adding 127 with the exponent 1, that is 128. It's represented as 100000b in binary format. Okay. The sign bit S is 0. So you are combining the mantissa and as well as the exponent. So first you are writing the exponent here 1, 1, 2, 3, 4, 5, 6, 7 zeros. 1, 1, 2, 3, 4, 5, 6, 7 zeros. Okay. The before 0 is nothing but the signed bit. This one 0. After that 1, 0, 0, 0, 0, 0. And after that you are representing the mantissa. This is the mantissa. Clear? Any doubts here? Please let me know if you have any doubts. Okay, sir, 7 zeros, got it. Okay, fine. How do we get normalized form? Okay, 518 was asking me, what, where is the exponent part, sir? How do we get normalized form, sir? Okay, sir, can you explain the exponent? Please explain again, sir, the normalized form. Okay, okay, I will again explain the normalized form. Yes, this is the normalized form, right? We will see this anyway. Okay, for now, just try to understand about the about this one. So forget about this normalized form. We will see that in the evening class. Okay, I'll explain in detail how we will be getting the normalized form. Other than that, any other doubts? Please let me know. Okay, clear? Are you able to see my screen? Please see here. I am taking 2.5. No, just wait. I am trying to get it solved. Yes. Yeah, you can see here. I am taking the binary number 2.5. Am I right? I am taking binary number 2.5. I'm telling you the normalized form. Okay, I was searching for the annotations. I got it now. So please try to concentrate. So I'm taking 2.5. So the first number is 2, right? Please divide 2 with the 2 because you're going for a binary number. So when I'm dividing 2 with 2, I'll be getting 1 and the remainder is 0. Am I right? Yeah. Now 2.5, right? Now you take 5 and divide this 5 with 2. So when you divide 5 with 2, we'll be getting 2 and the remainder is 1. Now what are the reminders I'm having? For 1 I'm having 1 0. Sorry, for 2 I'm having 1 0. That is this one. And for 5 I'm having 1. And that I'm representing here 1. Is it clear? I again repeat. Please give me a minute. I will again repeat it. If still you are not able to understand, we will see in the evening session. Okay. So see here what I am doing. Yes. Just a minute. I am trying to get it. I'm not able to get the annotation here. Is it clear? My voice is not audible. Sir, again 2 is divisible by 2. Right, of course, it can be divisible. 0, 1. There. 4m. You are right. 2 is again divisible by 2. So if you go there, if you divide it again, you'll be getting 1, 0. And when you go for the binary part, you'll be getting 1, 0, 1 for 5. But you're not going for that 1, 0. You're taking only the first remainder. Anyway, exponent part, can you brief it, sir? We will divide only once. Yes, of course, till now we have understood that we are dividing only once. Okay, sir, okay. 61, I hope exponent part. What is the exponent part? Yeah, exponent part we have seen here, no? Just a minute. Yes, see exponent part, see. Oh. Yes, please read this. 127 is added to all exponents in the floating point representations, allowing all exponents to be represented by a positive number. So what I am doing here, I am just adding 127 to this. 128, where 128 in binary it is written like this. If you want, you can check 128 divided by 2. The same process what I have done just before with 2.2 and 5. So if you divide 128 with 2, you'll be getting this answer. Okay. I hope you're clear with it. Okay. Yeah, I think somebody has raised another doubt. Okay, sir, got it. Thank you. Thank you very much. 61. BD, was my voice clear now? Hope it is clear. Okay, anyway. Okay, so whatever doubts you are having, please keep the doubts on your book. Evening again at 4 o'clock we have a class at 4:20 to 5:20. We can discuss in brief. Okay, whatever doubts you are having, we can discuss there. Again, don't worry. Until then, at least try to understand what it is. Always remember, learning starts from the first step. Okay. So when you start learning, automatically you understand. If you're not able to understand, it's very good that you're going in the right process. Okay. And whatever doubts you have, you're always welcome. So I'm stopping the class for today. So, okay. Again, we will meet at 4:20. And whatever doubts you are having, we can discuss. And the last topic which I have not discussed, that is the floating point instructions. That also will be covered. Okay. Hope my class was very useful for you and was interesting. Thank you very much for listening my class.